Okay, let's look at a few examples of the general response in RL circuits to kind of wrap things up. Here we have an example of a circuit, RL circuit. Once again, we want to find IL of t, the current through the inductor for t greater than or equal to 0. We're assuming steady state for t less than 0. And we're going to apply the general solution, which only works for the current through the inductor. So in this case, let's go through and let's solve this circuit using the techniques we've learned before. Now, in this case, I've got a switch that's going to flip over from this position to this position at time t equals 0. And notice how I've drawn this switch. We give a name to this. This is called a make before break switch. Now, this isn't just something that I just drew just for the sake of drawing it. This is a switch that I included this switch because this is actually a parallel to a real switch that people would use in industry. Because think about it. Notice how this switch works. When it flips from this position to this position, there is an intermediate time when it's connected to both sides of the circuit before it flips over to the other. Now, why did I do it that way? Why didn't I simply do this? And just flip the switch over at time t equals 0. Well, think about that. If I'm flipping the switch, then there is going to be some very infinitesimally small amount of time when I'm going to be in between those two positions, flipping over. The moment I do that, my inductor is disconnected. The current goes to 0, current goes to 0, and V is equal to L di dt goes to infinity. So you can't do that. And for that same reason, you can't make an actual switched inductor do this, because the moment you try to flip over from one position to another, you get a huge spark. So instead, you do the make before break. So in this case, with the make before break, when you switch from one position to the next, you're never going to be in a situation where the inductor is disconnected at one end. It's going to go from one, it will make the connection, then it will break the other connection, moving to the other side. So this acts like a regular switch as far as we're concerned in this problem. But in the viewpoint of preventing this thing from arcing, when people build switches with large inductors in it, they will use these make before break switches. So just a little bit of industry explanation in terms of why this kind of switch is used. So anyway, let's go through and solve this. I want to find IL of t. Once again, let's go through and use our different steps. First of all, for t less than 0, we're going to find the initial condition. Once again, for steady state, we know that VL for the inductor is equal to 0 volts. So the inductor acts like a wire. So I've got 0 volts across it. And if I ground the bottom, what do we have here? So in this case, I've got 0 volts. I've also got 0 volts then across this resistor for t less than 0 because they're in parallel. And therefore, by KCL, IL plus 8 amps must be equal to 0 at this top node. And therefore, IL is equal to minus 8 amps for t less than 0. So therefore, the initial condition at time t equals 0 will be equal to minus 8 amps. So that's our initial condition. Then at time t equals 0, we flip over, once again with the make before break action, so the inductor is never disconnected. Now I flip over to this side. Now for the final condition, we're going to once again assume that t goes to infinity for the final condition. So we're going to find IF, and once again, as t goes to infinity, then the transients die out, and so di dt goes to 0, and therefore VL goes to 0 once again. So just as we saw before, we are in both a steady state condition for both t less than 0 and also as t goes to infinity. So in this case, we're going to have that this is 0 volts. Got 24 volts here. This is 0 volts. Clearly, IL is equal to that current, and IL is just going to be equal, as IL goes to infinity, t goes to infinity, this is going to be equal to 24 over 2 is equal to 12 amps. And that's our final condition. So initial condition, final condition are both found using the steady state assumption. Now let's go through and calculate the equivalent resistor across the inductor. Well, in this case, it's easy. For t greater than 0, the only thing connected across that inductor, if we zero out this source, is going to be that 2 ohm resistor. And so just by inspection, R is equal to 2 ohms. And so therefore, R is equal to 2 ohms by inspection. And therefore, tau is equal to 0.2 divided by 2 is equal to 0.1 seconds. And now, given tau, given IO and IF, I plug into this equation, and what I'm going to get is IL of t is equal to 12 times 1 minus e to the minus 10t plus minus 8 times e to the minus 10t. Just plugging in the initial, final values and tau, and what I get is this will be equal to 12 minus 20 times e to the minus 10t amps. And there is my result for t greater than or equal to 0. So, pretty straightforward. Initial condition, steady state. Final condition, as t goes to infinity, steady state. In both cases, the voltage across the inductor goes to 0. The inductor acts like a short circuit. And then we find the resistance across the inductor for t greater than 0. Okay? Let's look at another problem. And this is kind of an interesting one. Let's find IL of t and VL of t for t greater than or equal to 0. Once again, we're going to assume steady state for t less than 0. And we're going to do it for the following circuit. So here I've got an interesting circuit where there's only one source. And you look at that circuit and you might think, well, gee, if there's only one source, this must be either a natural response or forced response circuit. Don't make that assumption. Let's work it. Let's use the general response solution and work it. So in this case, this switch is going to close at t equals 0. Okay, let's go ahead. Let's find our initial, our final, and our tau values for I sub L. So in this case, solve for IL of t. So for t less than 0, let's find the initial condition. And so for t less than 0, this switch is open. And if the switch is open and I've got 0 volts across the inductor because it's in steady state, then in that case, the current I sub L is also flowing through both of those resistors. And I sub L is just equal to 20 divided by 1 plus 3 is equal to 5 amps for t less than 0. And therefore, the initial condition is equal to 5 amps. So here's our initial condition. Now let's look what happens for t greater than 0. So let's close the switch, go to t equal infinity, and let's find IF. So if I close the switch, what happens to that 3 ohm resistor? 3 ohm resistor in parallel with a wire is like a 0 ohm resistor. What's 3 in parallel with 0? It's just 0. So this wire in parallel with a 3 ohm resistor just becomes a wire. So now, what's IF equal to? Well, if VL once again goes to 0, then IL is just going to be equal to 20 over 1 is equal to 20 amps. And therefore, the final value is 20 amps. What is the equivalent resistance for t greater than R? Pardon me, for t greater than 0? Let's find my Thevenin equivalent resistance across C. And in this case, I zero out the 20 volt source. And what do you know? By inspection, R must be equal to 1 ohm. And so in this case, R equivalent is equal to R is equal to 1 ohm by inspection. And therefore, tau is equal to 0.08 over 1 is equal to 0.08 seconds. And now I can plug my values into my general response solution. And what I get is that IL of t is equal to 20 times 1 minus e to the minus 12.5 t plus 5 times e to the minus 12.5 t amps. And what do you know? It's a true general response solution. So even though I only had one source, I was still able to change the initial and the final value with that switching action. And if I combine my exponential terms, what I will get is this is equal to 20 minus 15 times e to the minus 12.5 t amps for t greater than or equal to 0. And there's my solution. Now I also want to know what VL is. What I cannot do is I cannot say VL is equal to initial condition times 1 minus e to the minus t over tau plus the, final condition times 1 minus e to the minus t over tau plus initial condition times e to the minus t over tau. Can't do that. I cannot write this equation. Can't do this. VL of t is equal to V final 1 minus e to the minus t over tau plus V initial times e to the minus t over tau. It doesn't work. What was the initial condition of the inductor before the switching event? It was 0. What was the final condition of the inductor, the voltage across the inductor as t went to infinity? It was 0. So if I try to use this equation, I just get 0 volts. Doesn't work. This does not work for the voltage across the inductor. What do I need to do instead? VL of t is equal to L DIL dt. That's how I'm going to find the voltage across the inductor. Take the derivative, multiply times 0.008, and what I'll get is 15 times e to the minus 12.5 t volts for t greater than or equal to 0. And there's my solution. So interesting little problem, because you're actually able to get a general response even though there's only one source in the circuit by changing the configuration with that switch. Okay, let's look at our final example. In this case, we're once again going to have a step function as opposed to a switch. And I'm going to find, once again, IL of t for t greater than 0. Once again, assuming steady state for t less than 0. So once again, looking at this, we're going to, since we're trying to find this for the current through the inductor, we can use the general solution equation. So what do we need to find? Initial condition, final condition, and the equivalent resistor, so we can, equivalent resistance across the inductor, so we can calculate tau. So let's go ahead and do that. So in this case, for t less than 0, let's find our initial condition, I0. And so in this case, for t less than 0, I've got a 10-volt source that's turned on. And in this case, I'm going to ground this. Now, I'm in steady state for t less than 0, so I must have 0 volts across this inductor. It's behaving like a wire, which means therefore I must have 0 volts at that node as well. And so in this case, what I'm going to get is I1, if this is 10 volts here, then I1 must be equal to 10 minus 0 divided by 5. Which means it must be equal to 2 amps. So I1 is equal to 2 amps. That means I've got a current-controlled voltage source. I must have 2 volts at that node. And therefore, what is this current? Well, in this case, the current must be equal to 2 minus 0 over 2. That must be equal to 1 amp. So when I write my KCL equation, what I get is that 10 minus 0 over 5 plus 2 minus 0 over 2, both going in, must be equal to I sub L. That's my KCL equation. 2 plus 1 is equal to IL. IL is therefore equal to 3 amps. And that is my initial condition for my circuit. Oops. So there's my initial condition for t less than 0. Okay. Now let's look for the circuit when t is greater than 0, or actually in this case, when t goes to infinity. After the switching event, let's let t go to infinity, and let's find IF. Let's find the final value. So for t greater than 0, this 10-volt source becomes a wire. It goes to 0 volts. So now what do I have? I've still got 0 volts here. Looking at this, if I've got 0 volts here and got 0 volts here, then I1 must be equal to 0. That means this must be equal to 0. That's equal to 0. I've got 0 amps here because I got 0 minus 0 divided by 2, and therefore IL is equal to 0. And that's my final value. Now, was this a surprise? Not at all. We've seen this before. What was the problem with this circuit? It has no independent sources. Therefore, I know that all the voltages and currents in it are going to be equal to 0. I went through and actually kind of did some calculations to prove it, but I could have just right at the beginning and said IL is equal to 0 because there are no independent sources. So my final condition is 0. Now what about tau? So for tau, I need to go through and find the equivalent resistance across the inductor. And in this case, we note this is equal to I1. In this case, we note I've got a dependent source, so I have to go through and I've got to solve using source driving in order to find the equivalent resistance. So here's a 1 amp source. I'm going to find VT, and therefore VT is the voltage of that node. This is I1, and in this case I can once again go through and write my KCL equation. So we find the Thevenin resistance across L for t greater than 0, and in this case 0 minus VT over 5 plus 1 plus I1 minus VT over 2 is equal to 0. That's my KCL equation. My dependent source variable equation, 0 minus VT over 5 is equal to I1. I can now go through and I can solve, and what I will get is that in this case, RTH, which is equal to VT divided by 1 amp, will be equal to 1.25 ohms. And therefore, tau will be equal to L over R will be equal to 0.16 seconds. And I can now go and plug these values in, and what I will get is that IL of t will be equal to 0 times 1 minus e to the minus 6.25 t plus 3 times e to the minus 6.25 t amps. And there is my result for t greater than or equal to 0. And since this is equal to 0, really what this is equal to 3 times e to the minus 6.25 t amps. And there's my result for t greater than or equal to 0. Now notice, the final condition was equal to 0. This was a natural response problem. I didn't even think about that, whether it was natural or forced response. As it turns out, since the final condition was equal to 0, it must be natural response, but I learned that after the fact because it turned out that the final condition was equal to 0 when I went through and did the calculations. So as I mentioned before, don't worry beforehand whether a problem is a natural or forced response or just a general response. It doesn't matter. solve for the initial condition, solve for the final condition, solve for tau. And then you will have your answer. Okay? So, some good results. Look at some of the practice exams and look in your book for more problems. But you want to learn this methodology. You want to learn to apply that general solution. As long as you learn this methodology and use it correctly, you will never see a problem you can't solve for a first order problem.